Hello, future aviators, and welcome to this explainer. I am Captain Pankaj. I'm a pilot, a flight instructor, and a ground instructor, and I've spent the last 17 years teaching across various countries. I want you to treat this like our own interactive classroom. Today, we are diving deep into the Ultimate General Navigation Masterclass, specifically tailored to prep you for your DGCA exams. We're tackling convergency today, so definitely get your notebooks ready.
You know, I always like to kick off my classes with a little aviation motivation. As the old saying goes, aviation is proof that given the will, we have the capacity to achieve the impossible. And I want that idea to anchor our mission today. We are going to translate these highly abstract 3D geometric concepts of the Earth into the precise mathematical rules you need to absolutely crush your DGCA exams, and more importantly, to understand exactly what's happening when you're up there in the cockpit.
To make this easy to digest, we've broken this complex subject down into a simple 5-part syllabus. Geometry, the math behind it, great circles versus Rhumb lines, the famous DIID rule, and finally, solving actual DGCA exam scenarios. Let's get right to it.
Starting with Part 1, the geometry of convergency and understanding the Earth's shape.
Right off the bat, it is absolutely crucial to realize there are two exact definitions you're going to face in your exams. First, there's the geographic definition. This says convergency is the angle of inclination between two selected meridians measured at a specific latitude. Because meridians meet at the poles and bulge out at the equator, this angle obviously changes. Then we have the navigational definition, which is simply the change in a great circle track direction between 2 points. Listen closely. Both are completely correct, and you absolutely need to know both.
To really lock this into your mind's eye, I want you to imagine the orientation of the meridian altering like a swinging pendulum as you fly east to west across different longitudes. Since true north is just the direction of your local meridian, your local true north is literally constantly shifting as you cross those lines. This single concept is the foundation of every calculation we're about to do. Okay, moving right into Part 2, the math. Specifically, the sine of latitude. Don't worry, I'll walk you through it.
The beautiful thing here is that this geometric shift of the meridians isn't just random, it's perfectly predictable math. This brings us to our core formula. Convergency equals your change in longitude multiplied by the sine of your mean latitude. And if you map it out, notice how it forms a perfect sine curve. Down at the equator, latitude is 0. The sine is 0, so your convergency is 0. But up at the poles, latitude is 90, the sine of 90 is 1, so convergency equals your entire full change in longitude.
Now, I want you to take a literal mental snapshot of this cheat sheet. If you've got a pen, write this down right now. Memorizing these common sine values, and I'm talking especially about the 0.5 value at 30 degrees latitude, is going to save you precious, precious minutes on exam day. You won't even have to punch it into your calculator. You'll just instantly know it.
Let's see how these math formulas actually dictate the physical path of your aircraft. In Part 3, great circles versus Rhumb lines.
It is essential that you can contrast these two paths. A Rhumb line gives you a lazy, constant track angle. That means you don't have to constantly adjust your heading, but the trade-off is you're flying a much longer, curved distance over the Earth. Great circles, on the flip side, give you the absolute shortest possible distance. This is exactly what modern FMS and GPS systems use. But the big catch? Your track angle is constantly changing.
If we visualize it, notice how the great circle track, the shorter path, is actually changing its angle relative to local true north at every single meridian it crosses. And why does it do that? Exactly, because of that swinging pendulum effect we talked about earlier. A straight line drawn in space is going to hit those non-parallel meridians at slightly different angles every time.
Well, that brings us to a massively important term for your exams, the conversion angle. This concept bridges the gap between those two flight paths. The conversion angle is literally just the angular difference between your great circle direction and your Rhumb line direction. And here is the magic formula. It is always exactly half the value of your convergency. Simple as that.
And to help with your spatial awareness when you're drawing these problems out, here is an absolute golden rule of thumb. Please remember this. The Rhumb line track is always closer to the equator than the great circle track. If you just make sure your Rhumb line is bending toward the equator in your sketches, you'll never second guess whether your track angle should be larger or smaller.
All right, moving to Part 4, the DIID rule matrix. This is how we track those angle changes. Enter the world-famous DIID matrix. This simple little cross diagram is going to instantly tell you if your track angle is going up or down as you fly. The vertical line separates westbound and eastbound travel, and the horizontal line separates the northern and southern hemispheres.
So, it stands for decrease, increase, increase, decrease, D-I-I-D. By memorizing this pattern, you can map any flight instantly. For instance, if you're up in the northern hemisphere and you're flying eastbound, your great circle track angle will increase. Lock this pattern in. It's going to be your ultimate shortcut on test day. Finally, Part 5, Solving DGCA exam scenarios. Let's take all this theory and turn it into a masterclass.
Now this is where my 17 years of teaching really kicks in, so pay close attention. I teach every single one of my students to follow this rigorous 3-step method so you never make silly mistakes. Step 1, draw the diagram. Always visualize it first. Step 2, run the math calculation using the formula we just learned. Step 3, apply your DIID rule to nail down the final answer. Let's look at this in action.
Let's step right through an actual DGCA problem. Say we have an initial track from point A to point B. Step 1, we sketch 2 meridians converging towards the north because we're in the northern hemisphere. Step 2, the math. Our change in longitude is 12 degrees. Our mean latitude is 45. So we multiply 12 by the sine of 45, which is 0.7071, giving us an 8.5 degree convergency. Step 3, DIID application. We are flying eastbound in the northern hemisphere, which means the track increases. If we left point A at 0.60 degrees, our onward track at point B is 0.68.5. If the question asks for the return track back to A, we just add 180 to find the precise reciprocal. That gives us 248.5 degrees true. Boom. That's exactly how it's done.
I'm going to leave you with this final provocative puzzle based on the mid-meridian concept we just explored. Your initial track is 300, and your final is 295. Can you visualize that pendulum swinging and calculate the midpoint answer right there in your head? Take a moment, think it through, and keep practicing these concepts. I am Captain Pankaj, and it has been my absolute pleasure guiding you through this general navigation explainer today. Keep studying hard, trust the structure, and I'll see you in the skies.